Hi, my name is Brandon Kramer.
And I'm Max.
And we did our project on the physics of guitars, more specifically guitar strings, and how differences in gauge and length of the string affect the sound wave it produces when struck. So the goal of this experiment was to find out the effect different strings of different brands and gauges had on the wavelength of the string. To achieve this, multiple strings were attached to the guitar and were struck and then analyzed with the vernier microphone and the vernier to analyze the wavelengths and the deviations between the trials.
There are a variety of natural frequencies, known as harmonics, at which a guitar string will vibrate. The natural frequencies of a guitar string are determined by the factors of the tension, linear density, and the length of the string. A standing wave is associated with each of these natural frequencies or harmonics of the string. There's a direct correlation between the wavelength of a standing wave and the length of a string. The wavelength associated with the harmonic frequencies can be found if the length of the guitar string is known. Therefore, the wavelength relationships and the wave equation can be combined to evaluate calculations estimating the length of a string needed to produce a given natural frequency. The wave equation is speed equals frequency times wavelength. The calculations can be determined to predict the natural frequencies produced by a known length of a string, which requires knowledge of the speed of a wave in a string. The disturbance in the air spreads out as a traveling sound wave. Ultimately, this sound wave causes a very tiny vibration in the eardrum, which is another story. At any point in the air near the source of the sound, the molecules are moving backward and forwards, and the air pressure varies up and down by very small amounts. The number of vibrations per second is called the frequency, which is measured in cycles per second or hertz. The pitch of a note is almost entirely determined by the frequency, high frequency for high pitch and low for low. For example, 110 vibrations per second, or 110 hertz, is a frequency of the vibration of the A string on a guitar. The A above the second fret on the G string is 220 hertz.
So the pitch of a vibrating string depends on 4 variables, one of them being the mass of the string. The more massive a string is, it will vibrate at a slower rate. So on steel string guitars, the strings get thicker from high to low, and then on classical guitars, the size change is complicated by a change in density between the strings. The frequency can also be changed by changing the tension in the string, using the tuning pegs at the top of the guitar, tighter giving it a higher pitch, and then looser giving it a lower pitch. The frequency also depends on the length of the string at which it is free to vibrate. In playing, you can alter the length of the string by holding a finger firmly against the fingerboard of the guitar, otherwise known as frets. Shortening the string, stopping it at a higher fret, would give it a higher pitch. Overall, the hypothesis of this experiment is a difference in gauge and length of a guitar string will cause a noticeable difference in the sound wave of a guitar string when played.
For the procedure, needed objects for the experiment are as follows: a guitar strings from different brands and different gauge sets, a Vernier LabQuest 2, a microphone, a tuner, and a guitar pick. To begin the experiment, different guitar strings of differing brands and gauges will be required. Remove the 6th string, or the E, from each guitar string pack. Initially, only these strings will be used for the experiment. Depending on the type of guitar, stringing techniques may vary. String each E string onto the guitar with each string belonging to its respective space, even if it's not in its place of where a different string should belong. The placement of the kinds of strings should be put in a sensible fashion. However, it will not have much effect on the results. The specific brand and gauge when selecting strings to use do not have to be specific, however need to vary from each other to test each brand and gauge individually. The order in which the strings are placed in this experiment are as follows. In 6th, an E-Elixir acoustic guitar string with a .056 gauge and ultra-thin nano-web coating and anti-rust plain steels.
5th, a C.F. Martin and Company traditional light bronze wound guitar string with a .054 gauge.
In third, an E. Ernie Ball custom gauge nickel wound electric guitar string with a .046 gauge.
And in the first position, an E. Martin Lifespan SP treated phosphor wound acoustic guitar string with a .058 gauge. It was also decided to use a B string with a lighter gauge to test a drastic change in gauge size, which came from the Elixir pack placed in the second string position.
Each string is tuned to E. The top string for standard tuning, E, A, D, G, B, E. To test each string at the same tuning, include the B string.
The B string is to be tuned to B and E in separate trials to test it in its natural tuning and along with the other E strings as well.
The difference in length is accounted for its placement of the guitar. Each string was struck with a guitar pick to produce its sound. A microphone, connected to the vernier, is placed in the center of the sound hole of the acoustic guitar approximately 2.54 centimeters from the string which was being played. The sound from each string was captured by the microphone and goes to the vernier to produce a graph of the sound wave. Each string was played 5 to 10 times to ensure the variety in trials. Each string should be hit with the same intensity of the pick. Trials with finger picking are to be taken as well. To analyze the change of length in a string, trials of playing strings with a finger pressed on the fretboard will be necessary to record. In this experiment, the frets of 5A and 12E, one octave higher, were recorded on the top string, E Elixir string. However, any frets can be utilized. All data acquired from the trials are to be compared with each other to look for deviations and similarities.
Our initial hypothesis was a noticeable difference in the sound wave of a guitar string being struck would be caused by a difference in gauge and length of the string. However, this was ultimately proven wrong in the experiment, being that there was not much of a difference in each of the sound wave of each note played in the trials. Regardless of a difference in gauge and length of a string from each of the E strings to even the B string, results determining difference in waves were inconclusive. Reasoning for the hypothesis proven incorrectly could be the fact strings do not account for much of the noise when played. The sound wave a plucked string produces is merely the slight disturbance in the air it causes, meaning various factors such as gauge, length, brand material, etc. are negligible. Therefore, this is why our hypothesis was proven incorrectly. There are a variety of factors which could have hindered the procedure as well. When stringing one of the electric guitar strings, it split the nut of the guitar in half, causing possible issues in the tuning of half of the strings. Some of the strings may not have been exactly tuned to E as well, being a few cents off, for example. This could lead to inaccurate comparisons in the trials between the E strings. The .058 gauge string was also a few months old, when all the other strings were only a day old. So this could cause a noticeable difference in the tone and sound wave, possibly. There was a noticeable difference in tone from the other strings, meaning it may not have been comparable. There also may have been other variables such as the gauge, length, brand material, acoustic, and electric, which may have been overwhelming for the experiment. So using less variables for the experiment may have helped the procedure. The microphone may not have been exactly in the same spot during each of the trials of the experiment, so this may have also hindered the trials. Overall, the difference in gauge and length of strings does not have a huge effect on the sound wave a guitar string produces when struck. This was proven through a multitude of trials conducted using a microphone and vernier to analyze the waves the strings produced. To also improve the lab, one should provide ample time to do the procedure, primarily to prepare for any time the guitar may be damaged during the experiment, such as a nut splitting in half. Results will be most accurate with a guitar in stable condition. Having a microphone stand to ensure it is in the same spot when conducting trials would improve the results of the lab as well.